ferromagnetic substances. Ferromagnetic substances are also known as strong paramagnetic substances. So, first of all, every atom is a magnet. Not only that, the atomic magnets are always grouped into domain. Domain, that means when you say domain, in one domain there might be the number of atomic magnets ranging from 10 to the power 17 to the 10 to the power 21 atoms. In one domain, all the atomic magnets will be in the same direction. That's why their magnetic moment will always combine to produce one strong magnetic moment. That means you could say that every domain behaves as a good magnet. But the thing is that these domains are not in one particular direction. In fact, they are randomly arranged. That's why net magnetic moment is not of much value. Even then, in normal condition, we find that these domains, despite being randomly arranged, they contribute to some magnetism, and that's known as spontaneous magnetization. These domains have their volumes ranging to this order, 10 to the power minus 2 to 10 to the power minus 3 centimeter cube. Now, how these substances behave in external magnetic field? You see, normally what happens, I told you that this is normal condition. The domains are randomly arranged and they are causing either no magnetization or very small magnetization. But soon as you place these substances in a strong magnetic field, what happens, all the domains rotate and become parallel to the external field. This whole process is reversible process. When you place the ferromagnetic substance in weak magnetic field, then what happens? The domain that is already parallel to the external field, that becomes very enlarged. So, this method is called the method of substitution. What does it mean? It means the boundaries, enlargement or their contraction, both the things take place. The domain that is parallel to the external field becomes larger. And in that case, you could say the process is not reversible. This is irreversible process. Transducer, you might have heard the name, that is used for producing ultrasound waves. Magnetostrictive transducers are used. That is based on this effect only, magnetostriction effect. What is that effect? When you place ferromagnetic substance along some external field, the length parallel to the magnetic field increases. And suppose this is AC, then in that case what will happen? The direction of AC will change, and that way this ferromagnetic rod will also start vibrating. That is the method of producing ultrasound. So, this is very important method or principle, you could say, magnetostriction effect. Only the crystalline substances can behave as ferromagnetic substance. If you are magnetizing ferromagnetic substances, you see, this is subject to external finite value, that's called saturation value. Beyond that, no ferromagnetic substance could be magnetized. You see how it behaves with temperature is given by this law. Above Curie temperature, Curie-B's law holds good, and you find here when you increase the temperature, susceptibility will, up to a certain point, this remains independent and then it starts decreasing. At Curie temperature, it happens that ferromagnetic substances become paramagnetic substance. Curie temperature for iron, nickel, cobalt has been given over here: 70 degrees Celsius, 358 degrees Celsius, 1150 degrees Celsius, and so on.